Perfect. Okay, yeah. Thank you for having me here. Of course, I'm really looking forward to seeing you all in person again. Yeah, I want to talk to you about the mass computation of meteoroids. And for that, we're going to have to talk about the luminous efficiency and see how much it still varies in the literature. And then I'm going to show you how that we can confine these values better by using the ablation method and combining them. And then I would like to talk to you about certain biases that can be introduced into the observation and also in the analysis, of course. Yeah, so the luminous efficiency, of course, is a value that's used to calculate the mass of a meteoroid based on its luminosity and how much of the kinetic energy is actually converted into the visible radiation. Yeah, it's used to compute optical data, meteoroid masses, but it's still quite poorly understood, even, especially considering how old it is and how much it's actually being used. Here is a list of just some various studies that have looked into the luminous efficiency for various mass ranges. So here you can see masses that range from 10 to the power of -6 to 10 to the power of 13 kilograms. And they actually find luminous efficiency values that vary between 0.02 and 40%. So there's a huge range between that, especially if you consider that most publications use only one specific luminous efficiency value to calculate their masses from their optical observations. So a different method to calculate the mass of an entering object would be the ablation method. Here we can have a look at the deceleration data of a recording, so the velocity over the height, as you can see on the right side here, and calculate the entry mass. For this, we do not need any assumption for the luminous efficiency, and overall there are fewer assumptions needed as well. This is actually what the FRIPON data does, one of the problems that we see is that fragmentation is of course neglected, which is a problem for most observations as well. Here's a formula that's used to find the brightness curve depending on the velocity, and from that calculating the coefficients or the entry mass of the object. We use a shape change coefficient mu and the luminous efficiency tau, and they are the luminous efficiency and the entry mass is proportional to the luminosity of the bright curve. Yeah, here you can see a light curve that was recorded by the FRIPON network. On the left, it's intensity over the relative velocity. And the shape change coefficient is supposed to be between 0 and 2/3, and the mass, the luminous efficiency, of course, between 0 and 100%. Yeah, they are found by using a least square fit to the luminosity data. If tau is smaller, it's correlated to a lower peak of the brightness curve, and actually the shape of the light curve changes with the shape change coefficient mu. Yeah, for that, of course, we need very accurate brightness information. And as you can see here, this is just one example. They usually vary by camera. So this is a magnitude that was recorded for various stations, and we do correct for those, but still the brightness information can be quite uncertain. So this is one of the uncertainties that's introduced into the data set. If we use those to calculate the luminous efficiency values, you can see the distribution here. And we found 281 FRIPON events that we want to apply these methods to, which have very good data. If we have a look at the calculated luminous efficiencies, we see that there is actually a dependency on these values dependent on the entry mass of the meteoroid. You can see our values here in blue. These are the blue dots. And other publications have found this relationship as well. Two very recent examples are the Supersinger and Campbell-Brown from 2018 and the CARPAC 2019 publication. These are also plotted in the plot here. I'm not sure if you can see it. It's the blue and the orange line here. What we find is quite interesting is that we have a similar shift to slope to their findings, but we have shifted values. So we would assume this might actually be due to the instrumental bias, maybe. And what's more problematic is that we find unrealistic luminous efficiency values around 100%. So of course we can't have 100% over 100% luminous efficiencies. So for this, we want to investigate some possible biases that introduce these unrealistic values. We had a look at quite a few different ones. These are the ones that we selected in the end to have a closer look at. So of course, there's the incompleteness of data recorded, deceleration, the final height of the object, the assumed meteoroid density, and then the flow regime that a meteoroid encounters in the atmosphere. So let's start with incompleteness. We just simulated a couple of incomplete light curves collected by the FRIPON network, for example. So we had a look what happens if we crop the beginning or the end of the light curve, or even both of them. Here you can see on the right side, on the bottom side here, this is the luminous efficiency values that were found for varying degree of fullness of the light curve or completeness of the light curve. And actually until 80%, for example, we have quite similar values that don't change very much. After that, it changes a bit, but still it's quite similar to the first values of that. And we actually find this for most of our data. So the missing parts of the light curves do not affect the computation that much. So we think actually this is a really great result and shows that our method is quite robust. Yeah, let's have a look at the deceleration data, which plays a little bit a role into this too, because if we have longer light curves are recorded, we can have a longer look at the deceleration. If the deceleration is larger, it's easier to calculate our results, and we had a look at relative velocity changes of over 80%. So these are only just these events remaining. And we find that if we have only these high velocity change objects, that all the small masses, or a lot of the small masses, and these large unrealistic tau values disappear. And we only have qualitatively good data events, we think. Yeah, we also looked at the height of the fireballs. There, of course, it's also connected if the meteoroid is able to penetrate deeper into the atmosphere, it can be recorded easier. It's longer to be recorded as well. So we have here looked at data points which with final heights lower than 55 or 70 kilometers. We find that we also lose all these really large, small masses and these unrealistic tau values. Yeah, so another really important point is the assumed meteoroid density. We think that this is one of the very uncertain parameters in all the calculations, of course. We tried to refine those a bit by using the shower association. For 99 events, we found a shower association, and on the left side, you can see the densities that we assigned to these showers. We looked at various publications for these, and they actually change quite a bit. So they are not even the same for different publications. So this is, of course, another uncertainty that's being introduced, but we still think it makes it a little bit more confined. So if we use these shower associations, this is the values that we got. And if we now have a look at all the other events, the sporadics that we could not assign a shower association to, we use a constant density for that. And here you can see how it changes with different densities assumed. So we start with 3,500 kilograms per cubic meter and end with 500. And as you can see, this, of course, lowers our luminous efficiency assumption. Yeah, so there's this, with decreasing density, we find that the tau values, of course, decrease, and we have an increase in the entry mass, which is what was expected just by looking at the formulas, of course. But we think this might actually be an instrumental bias or something like that. So this is a very interesting result that we think needs to be looked into as well. Yeah, so we find that there's a really strong dependency on the density, and we think we can refine it by using this stream association. Yeah, so one last thing that we looked at is flow regimes that are encountered by the meteoroids, we find that most of our objects based on the Knudsen number are located in the slip flow regime or in the continuum flow regime, and all our equations should be valid in the continuum flow regime, which is what we then use to further constrict our data set. So here you can see all the events that are in the continuum flow regime only. And we find that we again lose all these really small masses and find only the characteristic luminous efficiency values that work quite well. And also the slope was a little bit lower, of course, not that pronounced. Yeah, so from all these biases, we determined 3 of them to be the most useful ones, and had a look at what of our data points fall into these 3 categories. So we have these really high velocity value events with a low end height, and a continuum flow, which shows that, that they are in the right atmospheric options. And we find that these work for 54 of our events that we analyzed. And this is then the final data set that we think is actually quite, let's say, pre-biased. So we should not encounter that many biases in this data set as well, which renders a great data set for further analysis. We find tau values that range from 0.012% to 1.1%, which are actually in a quite close range to the ones that found by Supersinger and Campbell-Brown and Kapek et al. Yeah, we published these findings in a recently published paper that you can find. And yeah, just a really short conclusion. So we looked at the luminous efficiencies of FRIPON meteors and studied all the dependencies and uncertainties in more detail. And we tried to find the most valid data points for the method and find tau values in the range of 0.012 to 1.1% when looking only at this pre-device subset. Yeah, thank you very much for your interest. And of course, please remember to smile for the photo in a bit.
Thank you very much, Theresa, for a nice presentation and good timing. So there is a space to applaud and questions raised by the real hand by Detlef Koschny. We didn't hear you, Detlef.
Yeah, not a question, but a comment. I want to point out that Theresa and also Esther, who you hopefully know, a few weeks ago received their PhD with an outstanding grade for, among other things, the work that you just saw. So congratulations, Theresa.
Thanks.
Good.